Okay, so this is the second part of the lecture on Project 4. And we're gonna, this is the security market line. You will have learned about this in 3318. Also in 3312 you would have touched on it. The security market line is kind of what we just did when we did our regressions, right? We just looked at, oops, that was funky. Not sure how that happened. We just looked at this in when we did our regressions. I'm going to talk to you in a minute about how the regression that you ran was a little bit different than that. But basically what you're doing is finding the beta for each security in this equation for the security market line, which is sort of the equation of the capital asset pricing model, or the equation that comes from the capital asset pricing model. And it says the security return is equal to the risk-free rate plus the risk premium on the market times the beta of that asset. Again, the risk premium on the market that's not exactly what we do, but I'll talk to you in a minute about how that's different. So if we assume the risk-free rate is 8%, just because the T-bill rate was 8% in the example before, it's kind of crazy because that's pretty high. And then the return on the market is 15%. Again, that's high. But we could estimate the required rates of return of all those securities that we looked at by looking at the required return on, or sorry, looking at the SML. So the required rates of return on high tech. The return on the market, of course, is 15%. We just plug in that 15 minus 8, 7% for each of those risk premium on the market, and we get the return on the market is 15%, which we already knew. The return on high tech is 17%. This is required rates of return, by the way, and so forth. Okay, so that's how we use the capital asset pricing model, or the SML equation of the capital asset pricing model. And I'm not going to really go through in 3318. Well, you will have talked about the required rate of return versus the realized rate of return, and so sort of what those differences are, and what happens when the required rate of return is not equal to the expected rate of return or the realized rate of return. You will have talked about that in 3318. We're not going to do that here. Okay, so what we did in your project was we looked at these 5 assets that you chose. That's the risk and return of each of them. I know it's not a dot, but that's the best I can do. And then we looked at the combination of those assets. So we combined those assets into various portfolios, pretend like those are dots. And it's easier to look at if you only look at 2 of them. If you looked at all 5 of them, it would be a little bit confusing. But I think if we look at 2 at a time, it's going to be easier. And so with different weights in the portfolio, like this could be one choice that you've made, this could be another choice that you made. I'm not hitting the line there because I'm using my finger instead of my stylus. But these are different combinations. The ones that are on the lines are different combinations of the assets in that portfolio. And so if we combine them in those different ways, what's changing here is the weight. So the difference between that one and that one is the weight of this asset and this asset in the portfolio. So the 2 different portfolio weights are what give you a different point on that line. And so we've combined all 5 of them, and when you do that, then you wind up with a whole bunch of different alternatives, right? And if you plot out those combinations for a whole bunch of different securities, then what you get is this minimum variance opportunity set, which I called in the other lecture, I called the envelope of the efficient set. The efficient set is the set of all, or I'm sorry, the feasible set. I didn't mean efficient set. The feasible set is all of these in here, okay? And there are actually more than just here. And the efficient set is this blue line, because you would never invest here if you could invest here, because you'd be getting a better risk-return trade-off. You'd be taking less return for the same amount of risk if you invested here than if you invested here. You get a higher portfolio return. So you'd never invest down here on the feasible set. You'd invest up here. And you'd never invest in an individual security in the feasible set, because if you did, you'd be choosing something suboptimal, right? You'd never select one of these guys. You'd select something on that efficient set. So the efficient set is the set of mean variance choices from the minimum variance set where given a standard deviation for no other investment, or sorry, wherefore given standard deviation, no other investment offers a higher return. So what I showed you on the previous slide. So now in 3318, you'll add risk and return indifference curves to that, and you'll pick an optimal portfolio for a person with various levels of risk tolerance. So this person has a different level of risk tolerance than this person. This person is actually less risk averse because they're willing to take this person is a little bit more risk averse than this person. This person is willing to take more risk for a not very big increment in expected return than this person. Okay, so this person is more risk averse. Less risk averse than this person. So now when you get to, there we go, when you get to the this topic in 3318, you're going to find out how you can add the risk-free asset to this portfolio and wind up with a straight line there, but I'm not going to go through that either. This is just the efficient set. We didn't add that risk-free asset in your project. So to estimate beta, we actually didn't use the equation that I gave you. We used what's called the market model, which is just the return on the security, some intercept that you estimate, and the return on the market, and you estimate the beta from that. It's called the market model. It's a pretty good estimate. The correct estimate would be to subtract the risk-free rate basically from both sides, so that you would wind up with, you'd really actually want to set that equal to 0 if you were really doing it. According to the capital asset pricing model, or the SML, but this adjustment uses the stock's return in excess of the risk-free rate. Very little difference in the results. It's really just different by a constant, so we almost always use the market model. So how does the CAPM test? Well, we find that betas change over time, and you did a little estimate of that. So you did one stock where you did the earlier returns and compared that to the more recent returns on that stock. And betas often regress toward the mean, and the mean, of course, is 0. The mean, of course, is 1. Not much of a problem for portfolios, more of a problem for individual stocks. If you look at Bloomberg, they use an adjusted beta where they're adjusting for regression towards the mean. So they actually use 2/3 of the estimated beta plus 1/3 of the mean beta, which is 1. CAPM doesn't work well with all assets. There is a linear relationship between beta and returns. The theoretical slope is quite a little bit different from the tested slope, and the intercept is a little bit different too. So those are the test results. This guy Richard Rawls said you can only test it if you have the true market portfolio, so we don't know if the model is wrong or if the index is wrong. And then Fama and French a long time ago said there's no relationship between beta and returns, and they also did some things where they added some extra returns to some extra independent variables to the CAPM, and that's called the Fama and French 3-factor model, or the Fama-French Hart four-factor model, which you may or may not study in 3316. You'll probably get them at some point in your studies here at Texas State. And that's about all I have to say about the capital asset pricing model and the project that you just completed.